Hello Math 1, I'm back for part 2 of the 3.1 videos. I'm just going to go through the examples on the notes and let's see if we can figure out what it means to solve the following inequalities, which means we just need to include an x with algebra, and then graph the solution set on a number line. That's the one where we plot either an open or a closed circle and then draw our lines either greater than or less than the solution. So let's get to it. Number 1. When you see 21 plus 3x is greater than 15, you should be reminded of those problems that we had in the last chapter. Remember when we had 21 plus 3x equals 15? So a trip down memory lane. Remember 21 plus 3x equals 15? Yeah, those were the days. That was all the way back in 2.1. You'd subtract the 21 from both sides. You got 3x is equal to negative 6. And then you divide both sides by 3. X ended up equaling negative 2 in that particular scenario. Well, here's the good news. You're going to do the exact same thing with an inequality. It's just you now have to keep track of a symbol that means greater than. So, we're going to take all the moves we did here and replicate them. Same thing. You're getting x by itself. Divide by 3. Don't mind if I do. Divide by 3 again. So dividing by 3 doesn't hurt the symbol. It's still greater than, and you get negative 2. So this is solving the inequality right here. We need an algebra solution. That's what I got. Now, how do you graph the number line, the solution set on a number line? Well, I showed you guys how that worked on the first video. You need to put at least 0, couple points to the right of 0, couple points to the left of 0. This would mean an open circle at negative 2. Greater than means all the numbers bigger than negative 2, which means right of it on the number line. Yeah. So, by the way, this is only one way in which to express that solution. I've had some students who like to just do that, which is okay. I just like this squiggle on the number line because it tells me it's every single point that exists on that number line. That's it. Check out number 2. All right, so see how x is on the left for this solution? Pretty much points us in the direction where we should be shading. That is going to be important because when you see x on the right, it usually points you in the wrong direction. So I'm going to rewrite it right away. I'm going to say 5 halves x plus 8 is, flip it, greater than or equal to negative 7. I think that's just easier for us to work with. So you can do that first. Again, solve it like it's an equation. Subtract 8 from both sides. You get 5 halves x is greater than or equal to. Remember, same sign means add them. And then if they're both negative, it's gonna retain its negative right there. Now, this can get tricky. You do not want to cross multiply when dealing with inequalities. I think one of your best option here is to put the negative 15 over 1 and just say, I want to find common denominators between 5x over 2 and negative 15 over 1. So make the denominator 2 on both sides. And there was a rule back in the solving equations chapter where if you had a common denominator, you could then ditch it. Same thing applies here. You can ditch the denominator. So that should be 5x is greater than or equal to negative 30. Yeah, divide both sides by 5. And you get x is greater than or equal to negative 6. So when graphing this on a number line, I'm just going to do it to the left here. I'm going to skip count. I don't want to put 6 notches left of 0. I'm just going to say, let's go by 2s. -2, -4, -6. So on the other side, I again have to go by 2s. It's 2, 4, 6. All right. Instead of an open circle for greater than, I'm going to have a closed circle for greater than or equal to. Again, reference the first video for explanations on that. See? Open, closed. Everything bigger than is going to go to the right of it. And that's it. Check out number 3. Seven minus 4x is less than 47. So I'm going to subtract 7 from both sides first. It's 0 minus 4x is less than 47 minus 7. All right, now something tricky happens here. When I divide by a negative number, so if I divide by red, something changes here, okay? Hey, think about this. All right, so here's a little thought bubble. Do you guys agree with me that -3 is less than 6? Hopefully yes, right? Now, what if I took that inequality and just decided off the top of my head, let's divide both sides of that by -3. On the left-hand side, you'd get 1. On the right-hand side, you'd get -2. One is not less than -2. So here's the thing. When you divide by negatives, you create this type of situation every single time. So unless you flip that symbol when you divide by a negative on both sides, you have an incorrect solution every single time. So here's what we're going to do. We divided by a negative. We're going to flip less than to greater than. And it's all because I divided by a negative on the bottom. All right. The graph on the number line, I think I'm going to skip count by 5s. 5, -5, -10. Open circle. Everything to the right. So maybe on the notes we should put, if you divide by a negative number, that'd be the same as multiplying by a negative number too. Remember to flip the symbol. So this becomes that. This becomes that. Only when you multiply or divide by negatives. All right. Now what happens on something like number 4 where we don't have just a regular x on one side with constants that need to be combined? This was almost like we just showed all the examples that were similar to 2.1 when you guys did solving equations. Here's 2.2. What happens when you have x's on both sides of the equation? Well, you collect the like terms just like before. If they're on the opposite side of the of the inequality symbol, you're going to do the opposite sign. So I need to get the 3x to the 24x. I'm going to subtract it. And at the same time, I can move the negative 15 to the right. Cancel on the right, cancel on the left. You get 21x is greater than or equal to 21. Notice I didn't flip the symbol because I didn't divide by any negatives. Don't flip the symbol because you didn't divide by a negative. 21 divided by itself is 1. So our solution is x is greater than or equal to 1. Closed circle. All right, let's check out 5. So what happens when we add grouping symbols? Similar to 2.3 from the last chapter. Well, you're still using the distributive property. You're taking 7 times 4x, and you're getting 28x. You're taking 7 times positive 2, and you're getting plus 14. Nothing changes from the solving equations chapter. Just like on the previous example, get the 5x to the left. And I think it's important now to think to yourself, I'm moving the x's to the left no matter what, because it's got to be on the left-hand side to draw the graph correctly. Okay, x is canceled on the left, constants x is canceled on the right, constants canceled on the left. 23x is still less than 15 minus 14, which is 1. All right, so then you divide by 23 to get a clean x. And remember, this isn't 23. This is 1 over 23. Right? And then some students are like, how am I supposed to graph that on a number line? 1 over 23 is like 0.04-ish, something like that. Well, there's a couple different ways. Here's one way. You could say, here's 0, here's 1, here's negative 1. 1 over 23 is so small that it's right here, just right of the of 0, okay? If it's less than, it's an open circle, and it's moving everything to the left. So all these numbers on the number line are solutions to that inequality. Another way you could graph it is you could literally count by 23rds. You could say, here's 1 23rd, here's 2 23rds, here's 3 23rds, and then do it in the opposite directions. That's a legitimate way of talking about your graph. So you don't have to graph both of these. I'm just showing you 2 different ways to represent. So just like with solving equations, we kept escalating things. We had grouping symbols on both the left and right-hand sides. Inequalities should be no different. Actually, pause the video and try this on your own. All right, let's see if you're correct. You take 3 times 4 to get 12. 3 times negative 2x to get minus 6x. The minus 5, still there. Less than symbol, still there. 2 times 3 is 6. 2 times negative 6x, or 3x, is negative 6x. In this situation, I'm going to get 12 minus 5 on one side, which is 7, is less than 6 minus 6x. Oh, interesting case here. Move the x's to the left. Move the constants to the right. X's cancel here. Constants cancels here, but this cancels as well. You got a special case. 0 is less than 6 minus 7. What happened? The x's canceled. That was two situations for solving equations. Remember, we had, was it no solution? Or was it all real numbers? This is where you read the statement. Is 0 less than negative 1? Is the value of 0 less than negative 1? That is not true. That is false, so you'd pick no solution. Interesting. So the special cases, they're still there as well. How about this one? The 6x just drops down, 4 times x. You should pause it and try this one on your own, just like the last one. 4 times x is 4x. 4 times 1 is 4. Notice we didn't try to combine these two at the very beginning. You get rid of parentheses first, generally. Still greater than or equal to. 2 times 3 is 6. 2 times 5x is 10x. Minus 12. All right, then you combine like terms on the left. 6x plus 4x is 10x. Combine like terms on the right. 6 minus 12 is negative 6. Then we move the x's to the left, the constants to the right. X's cancel on the right, constants cancel on the left, but the x's also cancel again on the left. So you're zeroed out on the left-hand side. On the right-hand side, you're left with negative 10. Another special case. X is dropped out. You have to make a decision. Is it no solution? Or is it all real numbers? Well, again, it's all about the truth of the statement. Is 0 a bigger than, a greater number than negative 10? It is. This is true. If it's a true statement when the x's drop out, it's not no solution. It's all real numbers. So you actually, I don't think you want to circle this as your final answer. That's going to be your final answer. All right, last one. I know this is a longer than usual video, but please stay with me. All right, last one. It's kind of asking a completely different question. Determine which of the following values of x belong in that solution set. So first of all, I want to see what the solution set looks like on a number line before I start asking questions about all of these things. I think I want x by itself. So if you see something like this, get x by itself first. Which seems pretty routine right here. X is on the left, constants on the right. So this is 3x minus 1x is less than 12. Divide both sides by 2. X is less than 6. Now, we didn't answer the question. We just figured out what x was when you get x by itself. So check out this number line. 1, 2, 3, 4, 5. Everything up to 6 is a solution. So the graph looks like this. There's an open circle at 6. Everybody left of that should be in the solution set. So, would x equals 6 be in the solution set? No. X equals 6 is not in the solution set. How about x equals negative 6? Yes, it's out here somewhere. See, left of 0. So x equals negative 6 does belong. So 6, no. Negative 6, yes. 0, yes, it's in the shaded area. 5.9, yes, it's just left of 6. 25 divided by 6, well, let's see here. 6 goes into 25, 6, 12, 18, 24. 4 times with 1 left over. 4 and 1/6, that's about right there. That's in the solution set. How about root 35? Well, root 36 is equal to 6. So root 35 is just left of that. Yeah, it's in there. Woohoo. 5 divided by 6, that's like a little bit less than 1. Right there? That belongs in the solution set. And then the last one, x equals 7. You are out of bounds, sir. So 1, 2, 3, 4, 5, 6. Those 6 belong in the solution set. Whereas these 2 on the ends, they don't make the cut. They do not live in the shaded region. All right. Wow, that was a lot. That was a lot to digest. But hopefully, most of it made sense in terms of if you know how to solve equations, you know how to solve inequalities. All right, thanks for watching, guys. And I'll see you next time for 3.2.